In this video, we're going to look at the concept that Max Planck used to fix the ultraviolet catastrophe, the quantization of energy. To help us conceptualize this, let's take a harmonic oscillator at rest. If we transferred energy to this oscillator via radiation, we can imagine that the energy rises continuously. But we are sneaking in an assumption here, that energy is a continuous scale. Planck asked the question, what if energy isn't continuous, but instead is discrete? So in that case, the oscillator would jump up the energy levels in steps instead of rising continuously. This would imply that energy can only exist at certain levels instead of all possible levels. It moves up in steps. We can refer to this step size as epsilon, and each possible energy level is made up of a pile of these energy steps. So, energy level 1, E1, has one of them, E2 has two of them, E3 has three, and you get the idea. So we could say that the energy at a specific level is equal to n, the energy level, multiplied by epsilon, the energy step. So, what does this idea imply for statistical mechanics? Well, if we look back to video 1, we explained how the Boltzmann distribution was used to show that the probability of a system existing at a specific energy level was proportional to this equation. So applying Planck's idea, all we have to do is swap out the E that stood for energy level in the continuous world for our new discrete formulation of E, n multiplied by epsilon. Substituting that formula in gives us a new formula that tells us the probability of a system occupying a specific energy level. We can visualize this probability distribution by doing a neat trick. If we take the value of the energy step size, epsilon, as a constant, and we imagine the temperature T at a fixed value, since K, the Boltzmann constant, is a constant already, we can imagine e to the power of the negative epsilon over kT as a constant at every energy level, and we can call that x. An interesting thing about this constant x is, no matter what we set the temperature or epsilon to, it will always be below 1, since it's an exponential with a negative exponent. When we substitute this constant x into our discrete energy probability equation, we see it can be rewritten as proportional to x to the power of n, which makes this equation a lot easier to deal with. We can now visualize this plot of the probability against each energy level. The rate of decay is dependent on the value of x. A smaller x decays faster, and a larger x decays slower, but the decay is always exponential. Just like in the continuous distribution, a lower energy level is exponentially more likely than a higher energy level. If we plot the corresponding energy level at each value of n, we can use this to help us find what the new average energy of an oscillator is within this quantized energy paradigm. We can multiply each probability weighting by the energy value at that weight, and add them together to give us the average energy. As we previously showed, Pn is proportional to x to the power of n. So we say that C is the coefficient of this proportionality, and say Pn equals C times x to the power of n. Since Pn is a probability, we can say that every possible value of Pn must add up to 1. Therefore, every possible value of C times x to the power of n will also add up to 1. Since C is a constant at every value of n, we can factor it out of the summing part of the equation. That leaves us with the task of finding the value of the sum to infinity of x to the power of n, which is actually a well-known geometric series. Let's define the sum to infinity of x to the power of n as s. Then we can calculate the first three terms. S equals 1 plus x squared plus x cubed. And it goes on in this pattern. So what would happen if we multiplied s by x? We would get xs, which is equal to x plus x squared plus x cubed, etc, etc. Now, if we subtract xs from s, something neat happens. Every term is subtracted apart from 1, and this gives us the equation s minus xs equals 1, which can be rearranged to give s equals 1 over 1 take x. Using our geometric series identity, we can rewrite the previous equation as c multiplied by 1 over 1 take x equals 1, which can be simply rearranged to c equals 1 take x. Plugging this coefficient back into our probability of an energy level equation, we get Pn equals 1 take x multiplied by x to the power of n. So that gives us a clearer definition of the probability of each energy level. Now we can combine this probability equation with the energy level equation to give us the average energy equation. We can refactor this equation to move most of it outside of the summing function. This gives us the sum to infinity of n times x to the power of n, which we can also solve as a geometric series. If we write the first two terms of this series, we get x plus 2x squared plus 3x cubed plus 4x to the power of 4, etc, etc. And this can be expressed as x plus x squared plus x cubed plus x to the power of 4 plus x squared plus x cubed plus x to the power of 4 plus x cubed plus x to the power of 4, and it keeps on going on like this. So remember how in the previous geometric sequence we worked out that 1 plus x squared can be expressed as 1 over 1 take x. We can use this to show that the top layer is x over 1 take x. The second layer is x squared over 1 take x, and it goes on like this, which means that we can write the sum equation as shown. We can factorise this into 1 over 1 take x multiplied by a simpler geometric sequence, and substitute the geometric sequence to give us the simpler equation, which simplifies further to x over 1 take x squared. So, we can now plug this geometric series identity into the average energy equation. This then cancels down into the simple equation, epsilon multiplied by x over 1 take x. Now if we plug back in the true value of x that we had assigned earlier, the exponential that acted as a constant, we get this equation, which then simplifies into our final average energy equation when energy is discrete instead of continuous. The average energy equals epsilon over e to the power of epsilon over kt minus 1. When we compare this discrete average energy equation to the continuous average energy equation, we can see it's quite different. The continuous formula is the equipartition theorem. We derived this formula in video 2 in this series. It's calculated by integrating the continuous curve to find the area within it, whereas for the discrete formula, we just calculated the area using sums to infinity and geometric sequences. Comparing the graph of continuous versus quantized energy versus probability distributions helps explain why each graph requires a different formula to calculate the area contained within it. So now we have the two different equations for the average energy of an oscillator. We can look at how this applies to electromagnetic radiation. If you remember, the intensity U of a specific frequency V of radiation at temperature T is proportional to that frequency squared multiplied by this average energy. This is because higher frequencies have more modes. These are the possible ways of that energy being distributed at this frequency, and each mode can be said to contain the average amount of energy. We showed this in more detail in the previous video, the ultraviolet catastrophe. So let's take a look at what this intensity distribution looks like under both the standard continuous energy theory versus the new quantized energy theory. Here are the two different equations. This pink curve shows the observed and experimentally confirmed radiation intensity distribution. As we discussed in the previous video, the classical prediction gave us a different curve entirely. But what about the quantized energy model? As the wavelength shrinks, the frequency increases, so the initial v squared part of the equation makes the graph blow up exponentially too, missing the experimental curve the same way that the continuous energy prediction does. But we have an extra degree of freedom to tweak now, and that is the value of this parameter epsilon, the energy step size. As we increase or decrease it, the rate of the exponential changes too. And if we break the yellow curve down, we can see it's the product of two other curves. The left side of the equation gives us a constant v squared curve, displayed here in blue. The right side gives us the constant value that doesn't change with frequency. The orange line represents this. So tweaking the value is changing the overall graph, but not in a drastic enough way. But Planck came up with a genius way to fix this, by making the value of epsilon dependent on the frequency. So, we say that E is proportional to V, and can be expressed as E equals HV, where H is just the coefficient to map that proportionality, now known as Planck's constant. Since epsilon is the exponent of the graph, at higher frequencies the orange line starts to decrease rapidly. This affects the overall shape of the yellow graph, and so as we change that proportionality constant, h, we can tune this exponential decay until the overall yellow curve finally matches the experimental blackbody radiation curve when h is at 6.63 times 10 to the power of minus 34. This means that the quantized theory of energy, something that Planck thought of as nothing more than a mathematical trick, predicts the intensity distribution of energy far better than classical physics, and this is the exact moment that I would pinpoint as the true birth of quantum physics. So, at lower frequencies, the energy probability distribution may follow the usual exponential pattern, but as the frequency increases, the minimum energy step size increases too, and the probability of that oscillator occupying a zero energy state increases dramatically, which is the real reason why the energy doesn't explode to infinity at higher frequencies. The cost to excite a higher frequency mode is higher than the cost to excite a low frequency mode. So this is how Planck solved the UV catastrophe, with the concept of energy quantization. In the next video, we'll talk about how Einstein took this mathematical trick and turned it into a more tangible reality with the photoelectric effect, and what this meant for the wave-particle duality nature of light.